Hello and welcome back. Today we begin the last two chapters of our second system of deduction. We're going to be looking at propositional logic in Chapter 7 and Chapter 8. Chapter 7 focuses on the nuts and bolts of propositional logic. We'll be learning new notation, and we'll be learning how to tell, or determine, I should say, when a sentence is true and when it's false, based on the meanings of the notation that we're going to be learning. We'll then take a look in Chapter 8 at how arguments in the propositional logic system can be used to facilitate sequences in a derivation. So let's go ahead and get started this week on Chapter 7, so the basics of propositional logic, and then next week we'll turn to Chapter 8, where we will study arguments in action. Let's get started. So you'll remember that in Chapter 5, we started looking at a system of logic known as categorical logic. We started there with categorical propositions, that is, statements in the categorical proposition form. We then went on in that chapter to look at inferences that you can make between categorical proposition types. Remember, for example, the square of opposition and other immediate inferences, conversion, obversion, and contraposition. We then went on in Chapter 6 to look at how you can take any three categorical propositions and combine them in such a way as to create a categorical syllogism. In Chapter 6, we learned two techniques for testing a categorical syllogism for validity. We looked at the Venn diagram method, which is useful in both the traditional and modern interpretations, and we also looked at the rules of the syllogism. Now in Chapter 7, we're going to look at sentences in a slightly different way. In propositional or sentential logic, also known as Boolean logic, we're going to treat sentences somewhat differently than we did in categorical logic. So what we need to do is learn a new language. Let's get started by defining what we're doing with propositional logic. We're going to take sentences that contain words like and, or, if, and phrases, and the phrase if and only if, and similar phrasings, and we're going to define them. So what will happen as we go forward is this: I'll start using words like connective and operator in place of talking about and, or, if, and only if in terms of words. So we're going to define these connectives, and then we're going to learn more notation so that we can basically reduce from the messiness of our ordinary language to the clarity of logical structure and only logical structure. So what we'll do is end up with not only definitions for these connectives, but also operators that basically define, by way of new notation, how these connectives work in a given sentence. Now, one of the ways in which we can think of propositional logic, also known as sentential or Boolean logic, is that it captures much more of ordinary language than is possible with categorical logic. Now, we'll find, if we move into a study of symbolic or formal logic exclusively, that when we learn quantifier logic, we get a sort of combo deal of categorical and propositional logic, and the resulting quantifier logic is really powerful. But what we're doing in this course is laying the foundation for further study, if you want, in formal logic. So what we're going to do is take sentences, simple sentences, and I'll define that in a moment, and we will combine simple sentences with connectives like you see above, and, or, if and only if, to form compound or complex sentences. And as you see in this third bullet point, the basic element of propositional logic is the statement, not classes of things. First off, let's say something about what I mentioned a little bit ago, logical operators. These are going to be the symbols that we use when we translate our connectives from ordinary language statement into the language of propositional logic. Let's also define a simple statement. This is what I mentioned just a moment ago when I said we take a connective and we compound a simple statement by way of that connective. A simple statement is the smallest linguistic unit in propositional logic. It is basically just a subject and a verb. So take, for example, the sentence H. H stands for, in this case, Hamlet is a tragedy. So Hamlet is the name of a Shakespearean play, and what we're saying about it is that it is a tragedy. The play is a tragedy. Of course, that sounds a little bit ambiguous, but we know that we mean by this Hamlet is a play that reflects a tragic sequence of events. Hopefully the production itself is not a tragedy. Anyway, when you take a simple statement and you combine it with a connective, you will get what's called a compound statement. So when you have a compound statement, you have at least one simple statement and at least one connective. So the sentence H stands for Hamlet is a tragedy. K stands for Kung Fu Panda is a comedy. You can put those two simple sentences together by way of the connective and. Now what we need to do next is replace the connective and with the symbol that stands for and. That is the logical operator for the connective and. We also need to be a little bit more precise about what we mean when we talk about a connective. The word and is an example of a connective, but we need to learn the formal language for words that reflect conjunction. So let's take a look at how this works in terms of talking about the operator, what we call the operator in logic, what its name is, so what the connective name is, and then the ordinary language words that we translate by way of one of these operators. So take a look at the far left column. We have a little squiggle mark. If you look at your keyboard, it should be in the upper left-hand corner. It's either at the tippy top of the keyboard or it's in the second row, but it still is in the upper left-hand corner. You also have a dot, which is typically found by way of doing some sort of option or command and then another key. There is a V. There's also what looks like a sideways U. And then there is what looks like an equal sign with an additional bar or an additional dash. So what do we call these guys? Well, the squiggle mark is called a tilde or tilde, and what it is called in terms of a connective, an ordinary language connective, is negation. So we use the tilde to translate sentences that include the word not, it is not the case that, it is false that, etc. The second operator is called dot, and it is used to translate any ordinary language conjunctions. So remember earlier I mentioned that the word and is a connective in logic. Well, it's a type of conjunction. The actual connective is called conjunction, and the word and is one of several conjunctions. So when you're conjoining two sentences, you're bringing two sentences together in a way that you are saying both are the case, you use dot. Wedge, or the lowercase v, symbolizes a disjunction. And a disjunction is a sentence reflective of an or either or unless compound statement. Then we have, lastly, our horseshoe and triple bar. Horseshoe is a conditional operator. In other words, it reflects sentences in the form of if this, then that, this only if that, and so forth. Now, one of the ways that you can think about these operators is that the first four are the most common. We rarely see in our ordinary language the triple bar in terms of the phrase if and only if, but it still is the case that it's really the first three out of which the last two can be constructed. So depending on what system of logic you learn, you might find that you spend a lot of time with the negation, the conjunction, and the disjunction before moving on to the conditional and biconditional, which are built out of combinations of those. But anyway, that's just an aside. The horseshoe, as I said, is the name of the operator that expresses a conditional statement. And conditional statements typically come in the form of if then or only if sentences. Lastly, the triple bar is an operator that we use to translate if and only if phrases, or sometimes you'll see more commonly, far more commonly than if and only if, you'll see a phrase like is a necessary and sufficient condition for. So take a look at the bottom example. We had H for Hamlet is a tragedy. We had K for Kung Fu Panda is a comedy. And then we have the connective and, which is a conjunction. And so if you look over to the right side of your screen, you'll see the translation H.K. Now, notice that one of the differences between what we were studying earlier and what we're studying now is this. We do not, in this version of propositional logic, translate separately or as part of the notation of the sentence the predicate, right? We just have H for the entire sentence. We don't have a relationship between, for example, the class of things Hamlet and the class of tragedies, right? Instead, we just have H for Hamlet is a tragedy. Now, in some versions of the system that we're learning, we might start with using H for Hamlet and then another case of T, not a capital T, but a lowercase t, for tragedy. Or we might have capital T for tragedy and lowercase h for Hamlet. And this would be a little bit more robust notation. It would introduce us to the predicate logic that is an important feature of formal or symbolic logic. Again, though, that's an aside. That's nothing for you to worry about unless you want to think about these things. Okay, now we're going to move on to each of our connectives, how we translate them from ordinary language into the symbolic notation, and then how we should read back our translated sentence. So whenever we have a rejection, a negation of some sort, we're going to use the tilde. Take, for example, the sentence, today is Monday. That is a simple sentence. A simple sentence is, in short, a sentence without a connective. A simple sentence is a sentence that can't be further reduced without losing its grammatical quality. So if you just said today, you wouldn't have a sentence, right? But saying today is Monday gives you a complete grammatical sentence. There's no connective involved, and so it's a simple sentence. You can compound the sentence, however, by saying today is not Monday. Notice that the negation goes to the immediate left of whatever is being negated. Couple of more examples. Gold is selling at $1,000 an ounce is G. It is not the case that gold is selling at $1,000 an ounce is negation or tilde G. Conjunction we've already seen by way of the word and. Conjunction says effectively both sentences on each side of the dot are true. So take a look at in red how many ways we have to conjoin. And, but, still, moreover, while, however, also, moreover, although, yet, nevertheless, and whereas. So when you start to rethink your language in terms of these connectives, you will see that when we see words like, for example, but, we might think of it as an acceptive word, but it still is adding to. It's saying thus and such and blah, 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 blah. So conjunction is expressed in quite a few ordinary language words, but it always asserts the meaning that both are the case. Both sides of the dot are the case. So take a look at, for example, honesty is the best policy and lying is for scoundrels. H.L. Now, you might wonder how we get the capital letters that we use for any translation. Typically what we do is we take the first letter of the subject in the sentence, and that becomes the simple sentence, the notation for the simple sentence. But we could choose any letters A through Z that we want. What's really important, though, is not the letter that you choose, but the consistency with which you choose it. So, for example, if you've already chosen H for Hamlet is a tragedy, and then somewhere else in your argument you have honesty is the best policy, you need to use a different letter. But if you're considering these sentences separate from each other, then you could use the same letter for respectively, Hamlet is a tragedy and honesty is the best policy. But whenever you're going to use a connective that brings two or more sentences together, make sure that unless the sentence is literally repeated, you use a different letter for different sentences that you need to notate. Notice also that the conjunction is always sandwiched between the sentences that it's meant to bring together. So you have H.L, F.E. You're never going to have a case, unless you've translated erroneously, where you have two simple sentences rammed together and the dot on the left or the right of the group. The dot's always going to be in the middle. The disjunction expresses, as we saw before, the or, unless, otherwise, either or. And like the conjunction, the disjunction is placed in between the sentences that it brings together. So Paris is the city of lights, or Big Ben is in London. She is either a Pisces or a Scorpio. Unless it rains today, we will go swimming. Notice that even though the word unless begins the sentence, it's still the case that because it represents a disjunction, we put it in between the sentences, it rains today and we will go swimming. Conditional statements, just like conjunctions and disjunctions, are translated with the operator in between the sentences that the connective brings together. So it's typically the case with conditional sentences that whatever comes after the word if goes on the left side of the horseshoe, and whatever goes after the word then goes on the right side of horseshoe. The left side of the conditional, the left side of the horseshoe, is called the antecedent. The ante, that means before. And the right side of the horseshoe, or the conditional, is called the consequent, or after. So notice that wherever the if appears, it's still the case that when you translate that ordinary language sentence, whatever comes after the if goes on the left side of the horseshoe. If you wash your car, then you can go to the movies. You can go to the movies if you wash the car. In addition, in ordinary language, many words and phrases indicate conditional statements. For example, every time, each time, any time, given that, provided that, and P implies Q. So what you want to do is think about your ordinary language sentence when you see connectives as looking at joints or hinges. I'll say more about that in a little bit, but your operators, which are the logical notations for your connectives, your operators are the joints or hinges of your sentences. Now, one thing that's a little bit tricky and worth pointing out, we'll spend more time on it a little bit later, is the difference between an if sentence and an only if sentence. Take a look at the sentence, if the neighbors are, or sorry, I'm reading the wrong one. If the light is on, antecedent, the light is on, then the neighbors are home, consequent, the neighbors are home. Whatever comes immediately after if, the antecedent, goes on the left side of the horseshoe, right? But what happens when you have the phrase only if? Only if the light is on will the neighbors be home. When you see the phrase only if, look at what comes immediately after that, and that's what you put in the consequent position. Now, there's going to be a little bit more to say about this in terms of understanding what this means, but for the moment, just make note of the fact that your standard if-then sentence is translated in the order that the if and the then appears, except when your if comes at the end of the sentence, right? Then you're going to put the whatever comes after the if on the left side of the horseshoe. But when you have a standard if this then that sentence, what comes after the if and what comes after the then are translated in the order that appears. The one exception is the phrase only if. Lastly, the biconditional. The biconditional is really as I'd mentioned earlier, there are sentences, conditional and biconditional, that you can build out of the other connectives, out of the other operators. Well, here is a really, I think, nice way to express that thought. The biconditional really consists of a two-way conditional. Another way that you can think of it is that when you assert the biconditional, you're saying you either have both or you have neither. So more on that a little bit later, but you can see in the example that there are two conjoined horseshoe sentences, and that is equivalent to the triple bar. And then what I just said, both or neither, means that if you have one, then you have the other, and If you have the other, then you have the one. In other words, the biconditional can also be built out of conjunction, disjunction, and negation. So take a look at the following. When you have an if and only if sentence, you have respectively an if then sentence where you have the antecedent and consequent. In this case, you eat your spinach, you get ice cream, and you have the conjunction, and then you get the only if, which is translated as follows, as we just saw. The only if, the sentence that comes immediately after only if goes in the consequent position. Now, remember, we're going to have some time to practice with this stuff. This discussion is really just meant to get you acclimated to the new language and to the meanings of these connectives. Okay, let's practice a little bit together. Don't forget, we'll have a separate practice video, but for right now, let's see what your comfort level is. I will stop by to visit only if I have finished my homework. So one of the things that you might want to do is mark up your work. In other words, if you're writing out this sentence on a piece of paper for your notes, walk through this with me in terms of marking up your work, and I'm going to show you what I mean. So what jumps out at us is the phrase only if. We know that only if tells us we've got a horseshoe. We also know that whatever comes after only if goes in the consequent position. So I'll use F for I have finished my homework. And how about S for I will stop by to visit. S, horseshoe, F. Now, another way you could tackle this sentence is to identify first your simple sentences and then look for your connective. It really doesn't matter, but don't be shy about marking up your page so that you can put on paper what you are thinking rather than trying to hold it all in your head. All right, let's see how we did. So in this case, V is I will stop by to visit, which is fine. That's just a different choice of a capital letter to notate the simple sentence. And H is I have finished my homework. Again, different choice of notation, but that's not important when you're dealing with just choosing which letter to use. There may be, as I mentioned before, considerations that should push you in a direction to choose one letter over another for a given simple sentence, but by and large, it's fairly arbitrary. Anyway, so we have I will stop by to visit only if I have finished my homework, and you can see that what we have, S, horseshoe F, is expressed here as V horseshoe H, but our translation is correct. So once you've got a handle on what a simple sentence is, as well as the basic sequence to translate a sentence from ordinary language into propositional logic notation, the next thing you want to do is make sure that each of your sentences is well formed. And a well-formed formula is just logic's version of a grammatical formula. So you need to make sure that, for example, your tilde is to the left of whatever's being negated. You need to make sure that your dot is always in between two sentences, that it's never, out front of a string of letters. So take a look at the following. In blue, you have two well-formed formulas, and in red, formulas that are not well-formed. So let me try to start with the red. What we have is and P, or conjunction P, and that's just meaningless, right? You can't extract meaning from that. You know what a conjunction is all on its own. You know that P stands for some simple statement, but put them together in that way and you have no meaningful statement. The second attempt says PQ disjunction. The third attempt says horseshoe P. Maybe if you want to be charitable, it says then P. And then lastly, we have PQ triple bar, or PQ if and only if. So you can see that there's nothing grammatical about any of these sentences. Now take a look at the ones in blue, and I'd like you to focus, because we need to talk more about this in a moment, on the way that I read the parentheticals. If either P or Q, then not R. If either P or Q, then not R. So notice that I've taken the P disjunction Q, which is in parentheses, and I have treated it, I've read it back as the antecedent of a conditional claim. You're going to notice that we need to use parentheses and brackets or braces to combine compound sentences into a unit. Now the second example, either it's S and P or it's Q and S. So let's say more about our well-formed formulas. We already know that the tilde's got to go in front of whatever is being negated. So we have a pretty good idea of what not to do. So I'm going to focus on blue. If neither P nor Q, then not R. We can also read it as follows. If not P or Q, then not R. Notice that in the first example, the negation, the first negation, denies the disjunction. The second negation denies the simple sentence R. Now take a look at the second example in blue. Either both S and P are the case, or not both, not Q and S is the case. We want to make sure always that we understand how the tilde works with respect to denying just one sentence, one simple sentence versus, let's say, a compound sentence. So go back to the first example. The tilde is in front of a pair of parentheses, and that's telling you that the tilde is saying no, or it's not the case, to that unit. On the other hand, the tilde in front of the simple sentence R just governs the R. So you can think about the parentheses as telling you something about the scope of the negation. Now take a look at the fact that the tilde can never be like conjunction, disjunction, conditional, and biconditional, a uniting operator. In other words, tilde just says it's not the case that. It does not bring together, either by conjunction, disjunction, conditional, or biconditional, two sentences. In addition, make sure that you use parentheses and brackets or braces as needed in order to identify what's known as the main operator. So take a look at the blue, P or Q and R, right? If you have your parentheses around the Q and the R, you're saying that this compound statement acts as a unit, and the disjunction governs or drives the sentence. Now take a look at the other sentence in blue. There's a negation that covers the entire sentence in brackets, right? So it's a negation bracket, and then all this other stuff, and then close bracket. If you were to eliminate the negation at the front, you could also eliminate the brackets, and you'd end up with two parentheticals whose main connective is, or the main operator is, the dot. All right, let's see if we can identify which, if any, of the following are well-formed. So for our first example, we have a pair of brackets that separate off a horseshoe, or sorry, that separate off the left side of a horseshoe from the right side, and the right side has a negation in front of an R. So thus far, this looks pretty good. Now let's go inside the brackets. We have a disjunction that's in between two sentences, one of which is simple and one of which is compound. The compound sentence, we can see, is separated off from the disjunction by way of a pair of parentheses, and there is a dot that conjoins the Q and the not P. So this one looks good. Second one, we have a negation in front of a compound sentence that is bracketed, so it's not this entire sentence. Now let's look within the brackets. We have a disjunction, so we're saying it's not either of these two sentences. And on the left side of the disjunction, we have a conditional in parentheses, and on the right side of the disjunction, we have a conjunction in parentheses. So this guy looks good. Now let's look at C. We have parentheses, or open parenthesis, R, dot, negation, S, disjunction P, close parenthesis. So we've got a problem here. We don't know if how the sentence should look. Should it look like this? R, conjunction, not S or P? Should it look like this? R, conjunction, not S or P? Should it look like this? R, conjunction, negation, S or P? Depending on which you choose, you're going to get a different meaning. And as we will see when we look at truth conditions for propositional logic, or for sentences that are written out in Boolean or propositional logic notation, we will have a different set of truth values. You can probably also see, so C is a problem. D is also problematic. We've got a negation that's not to the left of anything. We've got a pair of parentheses that are not serving to unite a compound sentence. Apart from that, the dot, if there was something well formed on the left side of dot, on the right side of dot, we've got a sentence that is well formed. So our big problem here is with the left side of dot. Let's check our answers. A and B, as we saw, are both well formed, but C and D are not. Now remember earlier I mentioned that one of the reasons why it's important to use parentheses is so that you can set off a compound sentence, or the elements of a compound sentence as a unit, as a single unit. And in doing so, what you're highlighting is a compound sentence's main operator. So take a look at each of these examples. In red, you'll see the main operator. There are sub-operators, and what we want to know is, as you're building a sentence, what the main operator is, so that at the end of building that sentence, you can determine that sentence's truth value. So when we're talking about a main operator, we're talking about the operator that drives or governs the sentence, and therefore also drives or governs the ultimate truth or falsity of that sentence. What's the main operator in this first example? Well, one thing that you can always tell yourself is the main operator is never going to be in parentheses. So that means all this stuff in brackets and parentheses are not going to yield the main operator. That means that the tilde is the main operator. Now let's look at the next example and then we'll check our work. The main operator is never inside parentheses or a parenthetical of any sort. And that means that here wedge is the main operator. Are we right? Yep. Yep. Good work. Now let's talk about how you can translate in such a way as to accurately reflect the logical structure of the sentence with the idea of finding the main operator. So take a look at the two examples here. The connectives are in red, and remember, either or serves not as two connectives, but as a single connective. So when you see either or, think wedge. And then the word but, the connective conjunction is circled. That's the main connective. How do you know? Well, there are a couple ways you can think about this. One is, take a look at the comma. When you see punctuation, commas, semicolons, that can tell you that the author of the sentence means that you basically a full stop, that what comes before that punctuation is a unit. And then secondly, an either or sentence, it means that you've got Tracy or Becky with respect to this owning a DVD player. What we don't have is a situation in which we're saying either Tracy owns a DVD player or Becky does, but Sophie owns one for sure, right? We don't have that rhythm to the sentence. Speaking of the rhythm of the sentence, you can, if you read out loud or if you pay attention to the cadence of your read, you'll probably be in pretty good shape with respect to identifying the main connective. You can also, not always, but very often, look to the beginning of your sentence to find the main connective. It's oftentimes the case, although as we've seen just now in the first example, that the first word of your sentence, if it is a connective word, is the main connective. In addition, if you have, as you have here, two connectives together, not and both, that the first connective is driving the sentence. Let's see how you're doing by way of this example. If Julian does not become a lifeguard at the YMCA or get the job driving school buses, then he will keep working at the bookstore in San Francisco and clean houses part-time. This is a pretty complicated sentence, but we can break it down because we've already got some tools to do that. You can identify your connectives You can identify simple sentences. You can identify punctuation. Really, what you start with doesn't matter. Try to develop a method that works for you. So I'm going to start by identifying connectives. I've got an if, then. I've got a not. I've got an or. And I have an and. So I've got a conditional, a negation, a disjunction, and a conjunction. The reason why I drew the line from the if to the then is because what is in between the if and the then is going to be on the left side of the horseshoe. That means that all of this stuff, there's a negation and a disjunction, all of this is going to be on the left side of horseshoe. I also can tell that this comma is going to play a role in what parts of the compound sentence go together to serve as a unit. But now let me go ahead and pick some letters. How about L for lifeguard, or Julian becomes a lifeguard at the YMCA? How about D for Julian gets the job driving school buses? And I'm just, what's the word that I want? I'm just giving us a shorthand, not the full simple sentence. So driving school buses. Then we have keep, or K, for keep working at the bookstore. And then lastly, how about C for clean houses part-time? Okay. What do we know about Julian becoming a lifeguard or getting a job as a school bus driver? If it's not the case that he becomes a lifeguard or gets the job as a bus driver, then he'll keep working at the bookstore in San Francisco and clean houses part-time. And notice that I need parentheses around both of these compound sentences. Now, you might be confused by the fact that I've put a negation in front of the parentheses rather than in front of just Julian does not become a lifeguard. But the sense of the sentence is that if we deny the lifeguard and we deny the job driving buses, what we're saying is that he does neither of these things, hence the negation out front. Okay, let's see what we've got. And don't forget, it may be the case that there is a different capital letter notation for each of the simple sentences. So we've got negation, L, disjunction D, horseshoe, B for keep working at the bookstore in San Francisco, and C for cleans houses part-time. We're moving on next to talk about how we can understand the truth value possibilities for each of these operators. So what we didn't do when we were discussing categorical logic was concern ourselves so much with the actual truth or falsity of a sentence. We don't want to have to do that. But there were times when we did, for example, under the traditional square of opposition, make assumptions about a sentence being true or a sentence being false to see if that would yield a necessary inference. What we're going to do in propositional logic is simply understand what the functions of each of our operators is, so that for any sentence governed by that operator, we'll be able to determine possible truth values. In order to do that, we need to create what are called truth tables. So before we get started on that, what you're seeing in blue is going to be the notation that we use when we're talking about any sentence in the universe. So what I mean by that is this. Notice that you've got lowercase p, q, r, and s. We use lowercase p, q, r, and s as a standard, at least in this textbook, for talking about any sentence that we could use, that we could make. So the sentence could be, Hamlet is a tragedy. The sentence could be, Julian works at the bookstore in San Francisco. In other words, it doesn't matter what the sentence is. What does matter to us is what happens when that sentence is compounded by one or more connectives. And what I mean by what happens is what the truth value of the sentence becomes where that sentence is a compound statement governed by a negation, a disjunction, a conjunction, whatever it may be. So first, take a look at the left side of the table that has a lowercase p in it and then a t and an f. What you'll always see when you see truth tables is the standard values. So any sentence in the universe is going to be either true or false. So we just write that in the left on the left side of that vertical line. So if any statement in the universe is true or false, that means that the negation of that sentence will have the opposite truth value. And I want to point out, because this is not visibly clear, that this F and this T, strictly speaking, belongs under the negation. So if a sentence is true, to deny that sentence is to say not P is false. So if P is true, not P is false. If P is false, not P is true. So let's take, for example, the sentence, Albany is the capital of New York, and that is true. If we assert it's not the case that Albany is the capital of New York, we're asserting a sentence that's false, right? So let's take another example. If I say Pierce College is in Woodland Hills, California, I know that sentence is true. If then I assert it's not the case that Pierce College is in Woodland Hills, California, the sentence is false. Notice the difference between the last slide and this one with respect to possible truth values. The negation denies a sentence. That sentence can be singular. That sentence can be compound. The definition of negation is fairly uncomplicated, and by that I mean the definition of negation is a two-row truth table. On the other hand, for the remainder of our connectives, we have four-row truth tables. So we define negation by way of a two-row truth table. We define conjunction, disjunction, the conditional, and the biconditional as a four-row truth table. And that's because conjunction, disjunction, conditional, and biconditional all require two sentences, one on each side of the operator. That in turn means that there are four possible combinations of truth values. Now, if you look once again at the left side of the vertical line, you see the lowercase p and the lowercase q. You'll see truth values that are laid out in a standard way. And by that I mean whatever logic text you pick up, you are going to have four possible truth values laid out as follows. P could be true and Q could be true. P could be Q, P could be Q, P could be true, Q could be false. P could be false, Q could be true, and lastly, each could be false. In other words, when you start with two sentences, you get four possible values, and the first one, in this case P, is half true, half false. Right? So I hope you're following along, but if there's any confusion, notice that we've got two values, right? Half true, half false, and then notice that Q alternates. And that's the way it's going to be every time we lay out a truth table. Now, though, let's look at what we're really here to make sense of, the definition of the conjunction. A conjunction is true when and only when each of the conjuncts is true. So conjunction makes a pretty big demand on our language. It says that a sentence that's governed by conjunction is true when and only when each of the conjuncts, each side of the conjunction is true. In all other cases, it's false. The disjunction is actually the opposite. It's a much looser connective. And I want to spend a little bit of time here talking about what that means and how we can understand our ordinary uses of the disjunction. A disjunction is false when and only when each of our disjuncts is false. In all other cases, it's true. Now take a moment to think about what this means for our ordinary ways of speaking about an or. We say that a sentence is true by way of the disjunction when at least one of the disjuncts is true. So if I say Mia wears glasses is true, then the sentence Mia wears glasses or the moon is made of green cheese is true. All I need is for one of my disjuncts to be true. And in fact, maybe both are true. I want you to remember this when we move into chapter 8 and we talk about some valid forms of reasoning. For right now, I'll just say that just because you have a disjunction doesn't mean that one and only one of the disjuncts can be true. So, for example, if I say today is Monday or it's raining outside, and I know today is Monday, that doesn't mean that it's not raining outside. In fact, both could be true. So if you're thinking about remembering the truth table, unlike the conjunction, which is true in one case only, the disjunction is false in one case only. So this is another way that you can think about what I just said. We've talked about this very, very early on. An inclusive disjunction is a disjunction that says one or the other or both can be true. If we want to assert an exclusive disjunct in terms of logical notation, we have to assert that one or the other, but not both, is the case. So as far as logic's concerned, if you have the sentence today is Monday or today is Wednesday, there's no reason why this sentence can't be true with the sentence today is Monday being true and the sentence today is Wednesday being true. After all, that's just row 1 of the truth table. If you want to assert exclusivity, you need to assert that so that the logic can understand that, if you will. In other words, you have to make explicit that you mean one disjunction can't be true. All right, 2 more truth definitions to go. First, the conditional, and then the biconditional. So if you want to think about the conditional in the following way, it might be helpful to you in understanding the truth table. You probably wonder why rows 3 and 4 come out true under the horseshoe. That seems a little counterintuitive, but think about it this way. If you go all the way back to your understanding of validity, you know that an argument is valid when it's impossible for the conclusion to be false if the premises are true. But take a look at rows 3 and 4 here. The premises, in this case, the left side of the conditional, are false. So it really doesn't matter what the conclusion is, or the right side of the consequent, the sentence comes out true, which is to say the argument is valid. So what I'm doing is I'm mapping the definition of the truth values for the conditional onto our understanding of a valid argument. We know that an argument is invalid, look at row 2 of the truth table here, when the premises are true and the conclusion is false. A conditional is false when the antecedent's true and the consequent is false. So you'll see when we do some practice how this plays out a little bit more. But for now, you might just think about it in terms of the following. The conditional, the row 2, I should say, mirrors the concept of invalidity. And the other remaining rows mirror the concept of validity. All right, lastly, the biconditional. The biconditional, as you can imagine, is like an equals sign. And by equals, I mean the truth values are equal. When you have one, you have the other, and vice versa. Or if you have one, or sorry, let me rephrase that. You have one, let me rephrase that again. You have both or you have neither, right? So let's think about it this way. Okay, so now we can take a look at the truth table. Notice that the biconditional, the triple bar, is true when the values are equal or the same. Okay, let's do some practice. Let's take the sentence X horseshoe Y. Not Y, sorry. And let us determine, based on our understanding of the truth table, what the correct answer is. So do you recall that the conditional is false in one and one case only? Do you remember what that is? If not, go back and take a look at your notes or follow along. If the antecedent is true and the consequent is false, then the sentence is false. But if the conditional as a whole is true, there are 3 ways this could occur. You could say that X is true and Y is true. X is false and Y is true, or both X and Y are false. Okay, let's practice a little bit. We have the following sentence: if X then Y, or X horseshoe Y, we're told that it is true. And if that's the case, which of the following is correct? Must it be the case that X is true, that X is false, or could X be true or false? Well, let's answer by way of a truth table. We know that there's one situation in which the horseshoe is false, and that's when the antecedent is true and the consequent is false. But there are three ways in which the sentence comes out true. If each of the antecedent and consequent are true, if the antecedent is false and the consequent is true, and if each of the antecedent and consequent is false. So if we say that the sentence is true, we can see that X, or P, whichever you prefer, could be true or it could be false. It doesn't have to be true, because there are two other cases in which it's not true and the sentence as a whole still comes out true. So our answer should be C. And we're correct. Now that we understand how to translate sentences from ordinary language into propositional logic notation, and we understand our definitions for each of the operators, in other words, we know under what conditions a negation, conjunction, disjunction, conditional, and biconditional are true or false, we can now move on to looking at how we can determine possible truth values for any sentence. So first we need to understand what sort of truth table we're going to construct. And by that I mean we need to know how many rows of a truth table we need for a given sentence. So the way that you determine the number of rows of a truth table for a sentence is by way of each of the simple sentences. In other words, take a look at each of the examples below. In the first sentence, we have two simple statements, P and Q. The fact that Q is reiterated a second time does not change the fact that it's the same sentence. So there are only two simple sentences. On the other hand, the sentence below that, which involves three simple sentences, will have more rows of the truth table. So what you understand, I hope, is this: the number of simple sentences, the number of rows that you have depends on the number of simple sentences in any proposition. Another way to put it is this: the number of lines in a truth table is going to be dependent on the number of simple propositions in the statement. So we end up with the following equation. The number of rows in a truth table is 2 to the number of simple statements. So in the first case, we have 2 simple statements. 2 to the power of 2 means 4 rows in the truth table, or 4 lines. 2 to the power of 3 means 8 lines, and so forth. So what we'll do in each case is this: you start with the leftmost sentence, in this case P, and if there are 4 rows or 4 lines in the truth table, you have 2 true and 2 false, and then Q gets half of that. In other words, you alternate true, false. With 3 simple sentences and 8 rows of the truth table, you'll again start with half true and half false for P, so 4 true, 4 false, and then half of that, in other words, the first 4 rows are divided, and you get 2 true, 2 false, 2 true, 2 false for Q. And then R, the last sentence, always alternates true, false, true, false, true, false, true, false. In other words, every first simple sentence is going to take half true, half false of however many lines in the truth table there are, and the last sentence is always going to alternate true, false, true, false. Let's go ahead and see how this works out. Remember, for the values on the left, we have our reference columns. So P and Q, whatever, regardless of what sentences we have, they can be A and B, they can be S and F, it really doesn't matter. They'll take half true, half false, and true, false, respectively. Now, how do we go about building our truth values? Well, we start with our simple sentences, and we're going to work from the least complicated of our compound sentences up to the main connective. So in this case, let me show you what I'm talking about here. Okay, so we have 3 connectives, the negation or tilde, the conjunction or dot, and disjunction or wedge. Which of these 3 is the main connective? Well, we know it's not the connective that's within the parentheses. That's because the connective within the parentheses or connectives within parentheses will never be the main connective. We also know that these parentheses tell us that this sentence's elements act as a single unit within a larger context. So we're going to calculate or determine the value of the conjunction first. We next notice that this negation covers only what's in the parentheses. The negation is saying no to the conjunction. So whatever values the conjunction has, we negate here. Lastly, we can see that the disjunction connects the left side with the right side. This is our main connective. We calculate it last by way of Q and the values of the negation. So let me pull this arrow over here. And I don't know if it would help you to see, now that I've walked us through this verbally, if it would make more sense now that we've got this last arrow to say that we take the values of 1 and 2 negates them. Okay, so what do we know about conjunction? Conjunction is true when and only when each of the conjuncts is true. So that means that we have a T in the first row or first line and false in the remaining 3. We then reject these values. False, true, true, true. And then lastly, we're going to compare these values under the negation with the values under Q. Now, if it helps you visually to keep order, you can always plug the values of your simple sentences underneath their appearance in a given sentence. And now we're in a position to make the determination based on the values that we've calculated or determined and the truth definitions for the disjunction. And we know that a disjunction is false in one and one case only, right? That's when both or each of the disjuncts is false. But that's never the case. And so this sentence is always true. It's what's known as a tautology. a sentence that is necessarily true or that can never be false. So let's walk through, by way of the slides, what we just worked through together. We identified the main operator, which is going to be calculated, or sorry, the truth values of which will be calculated or determined last. So we start with dot, we got that taken care of. Then we move on to the negation. We notice that the negation is always the opposite value of the sentence that's being negated. And then lastly, we see that, just as we discovered for ourselves, that the disjunction comes out true in every instance. Let's try another one together. So if we have two iterations of P and one iteration of Q, that means that we have two simple sentences. And these simple sentences, and because there are two simple sentences, we have a total of 4 rows of the truth table. The first column gets half true, half false. The second alternates true, false, true, false. Now we're going to set up our sentence in such a way as to highlight the main connective, the main operator. You know that disjunction is the main operator because it's the thing that's holding together all this stuff and P. Another way to think about why this is the main operator is because the operators within the parenthetical can't be the main operator. The horseshoe brings Q and not P together, and the tilde covers only P. When you think about the main operator, think about the operator that applies to every element in the sentence. All right, so let's get started. If we know that this is the main connective, then we know that we calculate or determine its truth values last. Of these two connectives, the horseshoe holds together the left side Q and the right side not P. So of these two connectives, horseshoe is the main connective, and that means we need to calculate not P first. So we're going to take a look at all the values under P and we're going to negate them. False, false, true, true. Now let's look at the horseshoe. The horseshoe is false when and only when the antecedent is true and the consequent is false. In all other cases, the horseshoe is true. Lastly, we compare the values of P with the values under, I'm going to change the color here, with the values under the horseshoe. And we end up with yet another tautology. It looks like we did quite well. We followed the proper order of operations. We first determined the values of tilde, then the horseshoe, and lastly the wedge. Now let's practice by way of propositions with assigned truth values. I think you'll find that this is going to be really helpful to you in reinforcing your understanding of the truth definitions for each of the operators. So let's assume you're given a sentence in the first case with 3 atomic sentences. And rather than constructing a complete truth table, suppose that you're told that R is true, S is false, and P is true. What your job is then is to determine the value of the sentence under these conditions. And as you can see, with horseshoe as the main connective, you first determine the value of S dot P, then you determine the value of R horseshoe S dot P. What about the second example? What if the truth values are not assigned to every proposition? So suppose that you are given the sentence P dot Q and you know that P is true. If P is true and we don't know what Q is, we don't have any way of determining what the sentence's value is. Why? Well, because for this particular sentence, there's one and only one way for the sentence to be true, whereas there are three ways for the sentence to be false. So absent having an idea of what Q is, there's no way for you to determine the value of the dot sentence or the conjunction. All right, let's go ahead and practice this ourselves. And then we'll check and see whether or not we've got it right. Okay, so we're told P is true, Q is false, and R is undetermined. In other words, it hasn't been assigned a truth value. We also know that the main connective of the sentence is, or the main operator is the horseshoe. The sentence says, if P, then either it's not Q or it's R. Okay, so since this is the main connective, we're going to determine its value last. If we just look at negation Q, disjunction R, we know that the negation covers only Q, so that means that we determine this value first and the disjunction second. Again, we're assuming that we can do this absent the value of R. So we know that Q is false, which means that not Q is true. Now, since not Q is true, it doesn't matter what the value of R is. Why is that? Because we know that disjunction can be true in three ways. Either the negation can be true and the R can be true, the negation can be true, or the R could be false. So in either case, the disjunction comes out true. Lastly, we already know now what the value of the disjunction is, and in fact, we don't need, therefore, to know the value of the antecedent of the conditional claim. That's because a conditional is going to be true when the consequent is true. Remember, there's one and only one way for the conditional to be false, and that's when the antecedent is true, but the consequent is false. So if the consequent is true, it doesn't matter what the antecedent is, but we're given its value anyway. All right, let's go ahead and check to see if our work is correct. You'll notice that we've got all the right values and we have completed our determinations in the right order, and we've come up with the correct value for horseshoe. Okay, this is the last bit of material that we need to cover for Chapter 7. You've already done a lot of work. I think it was important, though, for us to do it all in one sitting because of the way that this material builds. Having said that, you could certainly separate out watching the video over a series of days if that helps you. So we know how to translate from ordinary language into propositional logic notation. We know how to determine a main operator when we have more than one in a compound sentence. We know what the truth definitions are for each of our operators. And we know how to set up a truth table to determine the truth values of a given sentence. The last thing we need to do is talk about how we can determine whether or not an argument is valid. So recall the definition of validity. An argument is valid when it's impossible for the conclusion to be false if the premises are true. So what we do by way of a truth table is look for a row on which the conclusion is false while the premises are true. If no such row exists, if no such combination of values obtain, the argument is valid. And I'm going to ask us to go back to a discussion that we had earlier about the disjunction so that you can, I hope, more clearly see what I mean. Okay, so here is our argument. We have the premise, not both P and Q, the premise P, and the conclusion Q. And typically in a truth table, things are set up in this way. In other words, you get the premise or premises to the left of a slash or a double slash, and then the conclusion. You also get your referent columns to the left of the argument. So here, what we need to do is determine what the values are of, respectively, the dot and the tilde sentence. So the dot sentence is going to come out true on row 1 and false on the remaining rows. And then that set of values is flipped because they're negated. Let's work through this together. So P conjunction Q yields the following values. We then negate those values. And if it's easier for you when you're working along, you can always erase or scribble out the values that you use to determine the values under the main connective, and that way you don't get confused. You know exactly what you're looking at. We can then take P and Q's values respectively, because these are two simple sentences, and just plug them in. Now let's look at our rows. Is there a row in which or are there rows in which the conclusion is false? Yes. Row number 2. What about the premises? Are they true? I'm sorry, let me make that clearer. Yes, they're true. This argument fails on row number 2. The argument is invalid. So here we have each of the relevant columns boxed up, and you also can see the check mark next to the conclusion on row number 2 that shows the argument is invalid. All right, let's practice. We have two simple sentences, R and S. So we have two reference columns, and we lay out our values according to the standard method, which is the column to the far left takes half true, half false, and then the column to the right takes alternately true, false. Remember, if we have more rows, we will have more columns in between the so-called far left and far right. Now let's go ahead and write the sentences out. And I know that looks a little bit awkward, but it's not going to keep us from doing what we need to do. We know that this sentence, negation R, disjunction S, has two connectives, two operators. So since the disjunction is the main connective, we're going to calculate or determine our values for R, not R first. False, false, true, true. And then we determine the values of the disjunction by way of what's under the negation and the values under S. So we end up with true, false, true, true. Now we move on to our second premise, not S, and we're simply going to take the values under the referent column and reverse them. So we end up with false, true, false, true. And we do the same thing for not R. If R is true, not R is false. If R is true, not R is false. If R is false, not R is true. And if R is false, not R is true. Now we look to the rows where our conclusion is false. Is it the case that the premises are both true while the conclusion is false? No. Row number 1 has one false premise, and row number 2 has one false premise. So the argument is valid. It's valid because there's no row on which the premises are true while the conclusion is false. And you can see that our work bears out. Okay, now let's do a combo deal here. Let's practice with translating from ordinary language into logical notation for propositional logic. Then let's identify the premises and the conclusion. And finally, construct a truth table to determine if the argument is valid. So here's the example. If the government helped with student loan debt, students would not try to get good jobs. The government is not helping with student loan debt. I guess that's why students don't try to get good jobs. So first off, let's begin by identifying all of the argument elements, and what I mean by that is the connectives and the simple sentences. So we have the following. If the government did this other thing, then it's implicit, it's not stated. Students would not try to get good jobs. The government is not helping with student loan debt. That's why students don't try to get good jobs. Now let's try and identify each of the simple statements. And let's use G for the government helps with student loan debt. Let's use J for students try to get good jobs. And we end up with the following. I'm going to put it down here just so that we have a little bit more room. If the government helped with student loan debt, then students would not try to get good jobs. The next sentence is, the government is not helping with student debt. And the third sentence is, it's not the case that students try to get good jobs. Now, I think it's pretty clear that the last sentence is the conclusion. There's an inferential flow from the first two to the third sentence, even though we don't have any indicator words to help us. As you read the argument, the cadence of the argument, the flow of the argument leads us to it's not the case that students try to get good jobs as the conclusion. We have two simple sentences, G and J. So we have 4 lines of the truth table laid out per the standard. The main connective for the first premise is the horseshoe, which is not looking very horseshoe-ish, is it? The second premise has the connective tilde, or the negation expressed by the operator tilde. And then lastly, the conclusion is negation J. So first, let's determine the values for negation J. It's going to be the opposite of each of the original values. So not true is false, not false is true, not true is false, not false is true. We know that the horseshoe is false when and only when the antecedent is true and the consequent is false. In all other cases, the sentence is true. Not G yields the following values, and not J yields the following values. Now let's see if there's a row on which the premises are true while the conclusion is false. And there is. Row number 3. This argument is what's known as denying the antecedent. We'll see this in chapter 8. The argument is invalid. All right, let's check out our work against the key. And we've got it right. Good work, everybody. That was a lot of work, but it's really, really worth it. Learning this new system takes some time, so it's important to go over things slowly. We will do a lot of practice together. I will make sure that there is another video available to you this week so that you can work through all of the material that we discussed. And as usual, if you have any questions, problems, or confusions, let me know, let our tutor know. We have one more chapter or part of a chapter to get through, and then we're done for the semester. So congratulations on all your hard work, and I'll see you soon.